Strong acids. When we talk about the strength of an acid or a base, we're not talking about how corrosive it is. We're talking about whether it is a strong electrolyte or not. Does it make a lot of ions? So if we look at HCl, hydrochloric acid, and HF, hydrofluoric acid, we might think that those would be pretty similar. They're both binary acids, hydrogen and a halide ion. Fluorine and chlorine are both in the same group. They're right next to each other on the periodic table. These must be really similar. But there's something that's important that's different. Hydrochloric acid is a strong acid. And what we mean by that is it dissociates completely into ions. Hydrogen fluoride, hydrofluoric acid, is a weak acid. It does not do that. And there's no simple way to predict which ones do and which ones don't. But we need to know that strong acids ionize completely. So here we have illustration, HCl in the water, and it ionizes completely. We don't see any HCl molecules in the solution. Here's models, space-filling models. So we've got these hydronium ions and we've got chloride ions. We don't see any of the HCl molecules. That's what a strong acid does. A strong acid is a strong electrolyte. And when this happens, a 1.0 moles per liter HCl solution will have a hydronium ion concentration that is the same. Because if we look at this equation, HCl, all of that HCl goes to hydronium ion and chloride ion. So we could think of this as being like a pair of shoes. You've got a left shoe and a right shoe. If you have 10 pairs of shoes and they come apart, how many left shoes do you have? You had 10 pairs of shoes and now you dumped them in a box or you threw them all over the floor and they're separated from their mates. We still have 10, right? You've got 10 left shoes and 10 right shoes from the pair because they came together. So here, all of these come apart. None of them stay together. And so, however many moles of these, I'm sorry, I should start over here. However many moles of HCl we have, that's how many moles of hydronium ion we're going to have. So the concentration is going to be the same. We did a demonstration like this in lab. We used slightly different apparatus, but same idea. We saw that here we've got the electrodes, and this is pure water, distilled deionized water, just water. Doesn't conduct electricity, the light bulb doesn't go on. You throw some hydrochloric acid in there, and the light bulb glows. This is a strong electrolyte. It forms lots of ions for that to carry the electric current. We're going to learn about 6 strong acids. There they are. You know that it's a strong acid because it's in the list. If it's not in the list, it's not a strong acid. Okay? We talked a little bit about these words monoprotic, diprotic. This is a diprotic acid because it says H2. So both of those hydrogens at the beginning of the formula are ionizable, so they can both come off. Monoprotic, those contain only one. So the rest of these guys in this list are monoprotic acids. Monoprotic, 1 proton. The weak acids do not completely ionize, and so there are very few ions. They are weak electrolytes, which means they do not conduct electricity well. So here, when we put hydrofluoric acid, a weak acid, into water, it does form some ions, but this is an equilibrium. This is a partial ionization. It does not go all the way to the right. We're not going to care how far it goes. We're just going to know that it does not go all the way. So if we look at the pictures for HF with the formulas, we see that here's hydronium ion and a fluoride ion, but most of them remain the molecule. And with the pictures, the models, we see the same thing. we do have intact molecules. With a strong acid, you don't. They all come apart. There, again, is the light bulb not glowing. If we put hydrofluoric acid into the beaker, it will glow, but only a little bit, which shows us visually that there are a few ions. There's some ions in there. It does form ions, but only a few, as opposed to the hydrochloric acid that formed a lot of ions. There are a lot of weak acids. Anything that's not on that table of strong acids is a weak acid. These are just a few. Hydrofluoric acid, acetic acid, phosphoric acid, carbonic acid, those are some we may have mentioned. A couple of these are diprotic. Phosphoric acid is triprotic. So if we look at diagrams like this, we can identify which ones are strong acids and which ones are weak acids. Here we've got iodide ions and hydronium ions. Are there any other type of ion in there? Or any other type of particle? No, all we have are the ions. So that must have been hydroiodic acid, and it ionized completely. So is this strong or weak? That one's strong. How about this one? We've got two kinds of particles here. We've got nitrate ions and hydronium ions. Strong or weak acid? Strong. It all dissociated. Over here we've got formic acid. So we've got some hydronium ions, and we've got some formate ions, but we also have a lot of these molecules. Strong or weak acid? Weak acid. It does not all come apart into ions. That's what a weak acid is. So these are, personally I think these are kind of dumb questions to be asking, but here they are, so we're going to do them anyway. What's the hydronium ion concentration in each solution? The thing we have to ask ourselves first is this a strong acid or a weak acid? This is a weak acid. If we look at the table of strong acids, it's not on there. This is a weak acid. What is the important thing about weak acids? How do they ionize? Not completely. So this will ionize, it's monoprotic, we'll have a hydrogen ion and we'll have the rest of this, but only a little bit. So can we actually calculate how much of that there will be, how much hydrogen ion? See, the basic thing that we've got going on here is this. Do we have any way of predicting where the equilibrium is going to be? Not with the information that we're given. All we know is that there's going to be a little bit of this and probably more of that. So really all we can say is that this hydronium ion concentration is less than 0.5. So if it's a weak acid, the hydronium ion concentration or the hydrogen ion concentration, we use them interchangeably, not equals, less than 0.5. If it was a strong acid, it would be equal because all of the acid would come apart into ions. How about HI, strong acid or weak acid? That's a strong acid. So strong acid ionizes completely. So all of those are going to come apart. If we have 1.25 moles per liter HI and they all come apart, how many moles per liter of the H do we have? Just like the shoes. 10 pairs of shoes, they come apart, we have 10 left shoes, right? Or left. So the hydrogen ion concentration will equal the concentration of the acid that was put in, because it all came apart. How about letter C, HF, strong or weak? It's a weak acid. So then what can we say about the hydrogen ion concentration? Less than. It's going to be less than 0.75 because only a few of these are going to separate into hydrogen ions and fluoride ions. Most of them are going to stay together. So the concentration of hydrogen ions will be less than this, and that's all we can say. With more information, we can do a lot more, but that's something that you would learn in Chem 2. There are strong and weak acids. There are strong bases and weak bases. These are the strong bases, and the term strong means the same thing. They dissociate or ionize completely. These strong bases, what do they have in common? Just looking at their formulas. They all have hydroxide, right, as the anion, and a metal as the cation. So these are metal hydroxides. So we just use that as a general rule of thumb. If you see a metal hydroxide, you can assume it's a strong base. So we don't talk about diprotic or anything, but some of these have 2 hydroxide ions. So when strontium hydroxide ionizes, it forms 1 strontium ion and 2 hydroxide ions, right? So it's twice as many. If we look at sodium hydroxide, you put it in water, it comes apart completely into ions. You don't see any NaOH that's together. Same thing with the picture there. Weak bases are like the weak acids. Most of the weak bases do not contain hydroxide ion. They produce hydroxide ion by accepting a proton from water. And so you'll see something like this. This is a generic equation. Here B is the weak base, and it accepts a proton from water, forming BH plus and the hydroxide ion. And again, this is a weak base, and so this is an equilibrium, and it is not going to completion. Here's a specific example or equation for ammonia. Ammonia plus water. Ammonia is the base. It accepts a proton from the water molecule, becoming ammonium ion. And then the water, after it is donated a proton, becomes hydroxide ion. But again, there's this equilibrium. And so if you see an equation like this with an equilibrium arrow, then it's definitely going to be a weak base. And the pictures, again, here we see a lot of the intact molecules and few ions. A lot of the intact molecules, only a few ions. There are lots of weak bases. Here's some examples. And you'll notice none of these are metal hydroxides. So let's look at these. Similar type of question. What is the hydroxide ion concentration in each solution? Again, we need to ask ourselves, is this a strong base or a weak base? Barium hydroxide. Even if we don't remember exactly which metal hydroxides were on that list of strong bases, this is a metal hydroxide, right? So a good guess would be strong base. And then what does this do when it dissolves, when it ionizes? So hopefully now that we've been through the whole semester, you can look at this and recognize, okay, this is one ion, and then this inside the parentheses is another ion, and outside the parentheses is a 2, meaning I've got 2 of those. So when this comes apart, I've got a barium ion and 2 hydroxide ions. It's a little bit like a bicycle. Well, this will be ugly. It kind of looks like a bicycle. If we take the wheels off the bicycle, right, then we've got that really messed up looking frame. And we've got 2 wheels, right? For every barium hydroxide that ionizes, we get 2 hydroxides. It's a strong base. It comes apart completely. All the bicycles come apart. All the wheels come off the bicycles. But we end up with twice as many wheels as we had bicycles, because each bicycle had 2 wheels on it. Does that make sense? So then, if it was 0.055 moles per liter bicycles, what's the concentration of wheels? It's going to be twice as many, right? Because we're getting 2 of these for each one of those. So it's that concentration times 2. Let's jump down to the bottom and do this one. 0.45 molar sodium hydroxide. Strong base, weak base. Strong base. So strong base, let's think, you don't actually have to write this out, but it can be helpful. Excuse me, there's a sodium ion and hydroxide ion, right? This would be, I guess, a unicycle, right? There's 1 frame and 1 wheel. It comes apart, you have the same number of wheels. Or we could go back to the shoes. There's the left shoe and the right shoe. For every pair of shoes that you started with, you have 1 of each of these. So if we're starting with 0.45 molar sodium hydroxide, and all of it comes apart, what's the concentration of the hydroxide? 0.45. It's the same. So the hydroxide ion concentration is going to equal the same thing. So for the strong acids and the strong bases, we can tell something about the hydroxide ion concentration or the hydronium ion concentration from the concentration of the strong acid or the strong base, because we know it all comes apart. For the weak ones, though, we can't tell. C5H5N, strong base, weak base. It's going to be weak. So what can we say about the hydroxide ion concentration? It's less than 1.05. That's all we can say. That is not a 6.